Imagine that we have a circle that's rotating around its center at a rate of 1 radian per second. Okay, so I'm going to move this arrow for a second. This center, the center of the circle is the point O. There's another point on the circle, point A, and there's another point on the circle, point B. A is 2 meters from the center of the circle, and B is a total of 5 meters from the center of the circle. And we're going to imagine that the circle, there's a rotation going counterclockwise. Now there's two ways to measure the way point A and point B travel. One way is to measure their angular velocity. Angular velocity is represented by this Greek letter called omega. It looks like a little curved W, but it's not a W, it's called omega. So let's define angular velocity is the amount of rotation per unit of time. And the linear velocity is the distance traveled per unit of time. For those of you taking physics, that is known as displacement. So let's take a look at our point A and point B here. So let's look first of all, if we're moving at a rate of 1 radian per second, that means if I travel from here to here, then I've moved 1 radian. Okay, so this angle right here, oops, this is a 1 radian angle. Now, we could say that point A is moving 1 radian in 1 second, so that would be its angular velocity. But it also moves along here, this little arc. So this point is also moving a distance of 1 radius length, in this case 2 meters, in the same amount of time. So if we go down here, we can say the angular velocity of point A is 1, and remember I mentioned in the previous lesson that, or the previous section, that radians are a unitless measure. So I'm going to put it in parentheses. It's 1 radian per second, but technically the word radian isn't there. Now the linear velocity is 2 meters per second because that is how far the distance traveled of point A in the same amount of time. Now let's go to point B. So if we go out to point B, if we go from here to here in 1 second, notice that the angle amount traveled is still 1 radian, okay? The angular velocity of point B is still 1 radian per second. But its distance traveled now is different because the distance traveled by point B in the same amount of time is 5 meters, corresponding to its distance from the origin, because in 1 radian it's going to travel 1 radius length. So the linear velocity of point B is 5 meters per second. This corresponds to what we observed when we did our little example with the 3 students. The student in the middle here, one student represented the middle of the point of the circle, another student was this far out, another student was this far out. Well, as I had them all rotate in a straight line, the student on the outside had to travel a longer distance to keep that straight line than the student that was closer to the center. And the student in the center didn't travel any distance at all, but rotated. And so the person on the outside edge had to go much faster to keep up with the person on the inside. So the linear velocity had to be faster the farther away you are from the circle to stay on the same straight line. Now let's think about what's happening to the person, what's happening with the person in the center. The linear velocity of the person in the center, well, they didn't go anywhere. They didn't move any distance, didn't travel any distance. So that's going to be 0 meters per second. So the linear velocity is 0. But the angular velocity, the person rotated the same amount. So if you imagine everybody facing this direction to start with, and then everybody's facing this direction, if you think of 3 people in a row, they're all facing this direction, and they all rotate, now they're all facing that direction. They all rotated the same amount. So the angular velocity of point O is still 1 radian per second, just like points A and B. So what are the big ideas for this section? Number 1, every point on a rotating object has the same angular velocity, including the center point. Number 2, the linear velocity depends on the distance from the center, which is the radius. At the center, the linear velocity equals 0. Number 3, linear velocity equals the radius times the angular velocity if the angular velocity is in radians. This only works when the angular velocity is in radians. So pause for a minute and write that down, and then I'm going to show you using an example what this last point means. Okay, so let's put it in terms of our variables that we defined above. Linear velocity is v, we'll call radius r, and angular velocity is omega. And remember, omega must be in radians, or this formula is not valid. So let's look at our point B. So in point B, its linear velocity was 5 meters per second. The radius is 5 meters. Its angular velocity was 1 radian per second. So I wanted to illustrate, remember that radians is a unitless measure, which means then that the units match on both sides of the equation. We have 5 meters per second. I guess I should write second the same way on both sides. So we have meters per second on, well, I'll just put it this way, meters per second on both sides of the equation. So unless we have radians corresponding to the radius length, okay, because 1 radian gives me 1 radius length, then this correspondence works. And because radians are unitless, the units work out correctly. So we need to have both the correspondence, the one-to-one correspondence between radians and the radius of the circle, and we have to have radians be unitless for this relationship to work. So this is why one of the very most important uses of radians. We'll talk about more, the fact that radians is a unitless measure is also going to be very useful next unit when we do sinusoidal functions, but we'll get to that in next unit. In the next video, we're going to do a couple of example problems then using this relationship V equals R omega.